So this is a new video under dynamics of structure, and today we're going to talk about examples on single degree of freedom equation of motion. So we're going to talk about what we have explained last time, and we are going to explain it in detail using these examples. Okay, for the contents of today's lecture, we are going to have three main examples. The first one is going to be related to rod and spring example, and the second is going to be simple pendulum example, and the third one is going to be rotational spring example. So they are going to cover like different motions, and we are going to understand more if we apply what we have studied before. You're going to understand how to derive the equation of motion for different types of systems, okay? Whether it is like a rod and spring, whether it is a simple pendulum or rotational spring, okay? Okay, now let's go with the first example that we are going through it. So this is, let's say this is example 1. And this example, we are going to have a rod, as you can see here. Okay. This rod is having these equations, these dimensions. So we have like here, the length of it is L equal 10 foot, okay? And the diameter D of it equals to 2 inches diameter, okay? And the steel or E steel for this, which is Young's modulus of this bar, is 29,000 KSI. This example, you can find it in Shubra book 1.6, okay? Example 1.6. And K for one spring that is being attached here, okay, we put a spring here, and this spring is having or attached to it a weight, and this weight we are applying dynamic force on it. The weight of this or the mass of this box is going to be equal to, we know that the weight equal to mg. The stiffness of the spring that we applied at the end of this rod is 20 pounds per inch. 20 pounds per inch. Okay? So this is the system that we have, and we need to derive what is required is derive the equation of motion, okay, of the weight which is W. This W, we want to have the equation of motion for it. Okay? We only can have a hint here, neglect in your derivation, neglect the mass of the beam and spring. Neglect the mass of the beam and spring. This means that the only thing that we are going to consider its mass is the weight of this box, for example, here at the end of the spring. Okay, so now we have these are what we want to derive, and this is a hint for us. Okay. Now let's understand first, before going into anything, we need to understand how this system is going to behave in different cases. So for example, we're going to assume, first of all, this is, I'm going to call it case 1, which is we're going to have this beam, okay, and the spring is here and the weight is here. Here we are going to assume this is case 1, where that the weight, which is W, let's assume that weight is not applied. Okay, no weight. We are not putting mass on inside this box. And in the same time, we are not applying the P of T, which is P of T also. No, this is case 1. Means that the dynamic force is not applied and the mass or the weight of our system, or the weight or the mass, is not in this box. Okay, so there is nothing actually here. There is nothing is being applied here. After that, the second case is going to be the beam will deform if we apply if we're going to apply the weight of our object, and this is going to be case number 2, where that the weight is going to be applied. We can say that weight is, yes, means that applied, and P of T is going to be there also. Yes, okay. In this case, we are going to find there is a difference between the position that we have here and this position, right? This is going to be this distance. We're going to call it delta static. Delta static means that it is under static condition where that we apply only the mass, okay, and the force here is going to be W, okay, and it is toward or directing toward down, okay. We are going to have a static, we call this case static equilibrium. Static equilibrium. Where in this static equilibrium, we are going to find that we have weight applied on the mass, and there is another resisting force that is going to be developed in the spring itself. So if we are going to put here the free body diagram of our case here, for the second case, we are going to have weight downward, and we are going to have resistance force called Fs that is going to be developed in this spring, which is here. It is going to be Fs. Okay? We call this to be static equilibrium. Remember that I didn't put the dynamic load. Okay. Now case number 3, which is the last case where that we're going to apply our dynamic loading. So it is going to be so in this case we are going to apply the dynamic loading. Let's have another color here, which is P of T, and we are going to find that in this case we have, of course, we have the weight of the object, and opposite to this direction we are going to have the spring force, resisting force, right? Is going to be Fs. But there is something else, additional force that is going to be there in this system due to the application of the dynamic force, P of T. Can you tell what is this force that is going to be developed? If we have dynamic force applied on a system, what will happen for this system? What it will develop? If you look to the previous lectures, you're going to find that we are going to have what we call it inertia force, mu double dot, okay? Where this inertia force is going to make for us the dynamic equilibrium of the system at this case. Means that here at this level we are going to have this distance which we call this distance, we're going to call it U. U is like a variable distance that is going to take place because the application of the dynamic force. So this dynamic force is going to change with time, going down and up and down, and then we are going to okay, so here for this it should not be, yes, you are right. So in the second case, sorry, the P of T is not applied, so we say it is no, okay? And in the third case, we are having the weight, which is yes, it is applied, and P of T is going to be applied, yes, okay? So we have P of T here. So in this case, if we are going to put the equilibrium at this level, which is, we call it dynamic equilibrium, we call this case dynamic equilibrium, okay? Dynamic equilibrium. Here at this level, we are having different types of forces, right? We are going to have, if this is our system, then we're going to have different forces applied, as I put it here, put it in red color. So first of all, we have W, which is the weight of the system. We have the P of T, which is going to be the dynamic loading. We are going to have the F of S, which is the resistance force from the spring, and we are going to have something that is going to be developed in the system, and it is going to be the inertia force, which is mu double dot, okay? So this is the equation of motion for, or we can say this is the equation of equilibrium at each case, case 1, case 2, and case 3. So in case 1, let's put it, because it is, even that it's understood, but I'm going only to put it as redundant here. And I'm going to put, like here, there is nothing, I put 0, no weight, and also here 0. There is no resistance at all. So this is what we call it the free body diagrams for each case. Free body diagram, FBD. This is the free body diagram for each case. So in case 1, we do not have any forces applied in the system, right? This means that there is no weight because I have no mass inside this box. It's massless now. And we do not have any resisting force in this spring, right? Because there is no mass. So this system, there is no forces applied. In the second case, we have the beam is going to deform, and the spring is going to deform because we are going to apply the mass which is going to develop the weight or the force, which is related to the weight, and the spring is going to resist by Fs or some resistance force. We call it the elastic force or the resistance force, Fs. Okay? And then, in this case, we are going to have the third case where that we are going to apply P of t, which is the dynamic loading applied. And we have the original mass and Fs as it was in case 2. They are applied as they are. But when we apply P of t, the dynamic load, we know from previous lectures that there is inertia forces is going to be developed in the system. And it is going to be opposite to the direction of the dynamic load applied, right? Okay, so in this case, we are having this equation. Now, let's go for our solution. Okay, let's go to our solution. So I'm going to put my solution. Okay. After understanding our system, then we start the solution. The solution is we want to put an equation. From this equation, we want to derive the equation of motion. Then our case is going to be related to the last dynamic equation or dynamic equilibrium that we have put here. So we are going to say that f of s plus m, we're going to give this delta st plus u, are going to give it this designation u dash, okay, or u bar, as you can see it here. Okay, so based on this we can say that fs plus m u double dot bar equals to weight plus p of t, which is being applied. This is the equation that we have obtained under the dynamic equilibrium, right? This is what we have obtained. Okay, in this case, okay, we going to derive, the next step is going to be the derivation of this equation of motion, or at the equilibrium condition or the dynamic equilibrium condition, we are going to derive the equation of motion. If we look here, just I want to highlight two notes before the derivation. Notes, okay. Number one, the inertia force not present in the static equilibrium case. Okay, the inertia force is not present in the static equilibrium case. This is number one. Number two, the effective stiffness of the system is provided by the spring and the rod together. That's very important. Okay? When we look to this system, case 2 or case 3, we're going to find that there are two contributors here. The first one is the beam, and the second one is the spring. So we have two contributors. Whether in static equilibrium or in dynamic equilibrium, there are two contributors, the beam and the spring. So we're going to put it as a note to understand it well, that we're going to talk about I'm going to put it in uppercase, effective okay, the effective stiffness, okay, stiffness of the system. We're going to call it now the system, of the system. The system here means the beam and the spring. Okay? The effective stiffness of the system is provided by the spring and the beam together. Okay, and the beam together. Okay. And the third note, which is important, these beam and spring, if you watch the previous videos, these beam and spring, let's go back here, this beam and spring here, the beam and the spring, they are, you think that they are in series or in parallel? In series or in parallel? Have you watched the previous videos? No, huh? You have watched it? Okay, so these two systems or two contributors, they are in series or in parallel? In what? In series, yes, that's right. So in series, because, so we can write it as a note here. The beam and spring, they are arranged in series. What is the meaning of arranged in series? That as if that we have two springs attached together in this way. This one is our K, which is the spring, the original spring in our system, and this one is the beam, as if that we are representing it as a spring. So both of them, they are arranged in series. They are arranged in series. So in this case, K effective for this system, K effective for this system is going to be what? Do you know what is the ultimate effective stiffness of the two springs arranged in series? It is going to be K of the spring times K of the beam, right? Over K of the spring plus K of the beam. You will understand this if you go back to the previous video. Okay? You're going to understand this if you go back to the previous video. You will understand it. Okay, so these are the two important notes that we need to take care of. Okay, now let's go to the equation of motion again, and let's go to how we are going to derive it. So now let's go to deriving the equation of motion in our system. So we said that we have mu double dot bar, because we are talking about the bar. Bar, it is delta static plus u, right? Plus K effective of the system times u bar equals to the weight plus P of t. This is from what we have already derived before. Okay, this F of S, okay, it is the resistant or the resisting force. Okay, it is the resisting force. In this case, it is going to equal K effective of the system, right, times U bar. So it is the restoring force of the system, okay, going to be equal the effective stiffness times U bar, where this is U bar here, right? Because at the dynamic equilibrium, we are under different types of forces, right? And one of them is the resistance of the whole system. As we said, the system is consisting of two different contributors. One is the spring and the other one is the beam, right? So the effective stiffness of this system is going to be calculated as I have mentioned here, and then K effective is going to be equal to this, okay, this fraction. Based on this, Fs, which is the resistance of our system, equals to Ke times U bar, and then we have the inertia forces, which is Mu double dot bar, and the right hand side it is the weight plus P of t. Now let's go and write it in a neat way. So we have, this is our system here. Remember, from the static equilibrium condition, K effective times delta static equal to the weight, right? This is what we have mentioned before here in this case. Okay, so we are having the delta static times K effective. Okay, this Fs, it equals to, if we're talking about this case, so this means that we are having delta static times the effective stiffness of the system. So in this case, we can write it like here. That is from the static equilibrium. This is from static equilibrium. Okay? And then U bar double dot, okay? U double dot bar or U bar double dot, it equals to U double dot plus delta static. Is it right? If we go back to the, this is right. So U bar equal to delta static plus U, right? So, but actually, if we are going to look here, it is the second derivative. And this delta static, do you think that it is constant or changing with time? Constant, right? Yes, it is constant. It's not changing with time. Right? It is always constant. Okay? So we can't omit it here. What is changing with time is U. This U. It is going to be changing with time. Because this U, it is related to the dynamic equilibrium. If we apply the force, this means that this U is going to increase if it is going down, and then this U is going to decrease if the P of T is going up, right? But this static equilibrium condition, delta St, it is going to be the same and constant. So in this case, this delta static, I can say it is constant here. And in the derivation, we can say, if we say that U bar equal to U plus delta static, then the first derivative of U bar would equal to U dot plus 0, right? Because we are deriving it. And then U double dot bar equals to U double dot only, right? So this means that we are taking the constant is removed while that we're making the derivation. Okay? Okay. Now let's put our equation of motion, which is going to be mu double dot plus K effective of our system times U bar. It is going to be U plus delta static. This would equal to the right-hand side. The right-hand side is W, right? So W, which is this one, it is going to be K effective times delta static plus P of T, the dynamic loading. All right? Okay. In this case, we are going to rearrange this. We are going to find that K effective times delta static in the left-hand side is going to cancel K effective delta static in the right-hand side. We are going to rearrange it again, and then we're going to put it in this form, mu double dot plus K effective times U equals to P of T. This is our equation of motion. This is our equation of motion. If you look deeper here in this equation of motion, we're going to find that M, it is supposedly to be given for us, U double dot, it is, the meaning of U double dot, it is the acceleration, okay, of the mass itself. It means that U of T, okay, U double dot of T. And this means that U of T at any time here. And P of T, it is given for us. It is given. Whenever that we have an applied dynamic load, it is going to be given for us. The only unknown in this equation is K effective. We want to know what is the K effective of our system. Already, if we go back to our note, we have mentioned about our K effective. We can calculate it based on the spring stiffness and the beam stiffness. Okay, so now what we are going to do is calculate, so we can say this K here, it equals K effective equals to, here it is K times K beam over K plus K beam. Am I right? So now let's go and calculate the stiffness of the beam, because K spring is given for us, right? K, first of all, K of the spring, which is K only, we used it here, it was 20 pound per inch, right? It is given for us. So now we want to get what is the value of K beam in our case. So K beam, commonly it is going to equal from 3EI over L to the power 3, because we have a cantilever. Whenever that we have a cantilever, in this case, if you have a cantilever and you want K of this cantilever for unit displacement here, okay, if we have delta equal to 1 unit displacement, then in this case the shear stiffness that is going to be developed here, okay, it is going to equal 3E, which is Young's modulus of the material of the rod, times I, which is the inertia of the rod itself, over L to the power 3. And if you look to the example, you are going to find that we have everything about it, right? We have E, I, and everything. So here we have 3 times E, which is 29 10 to the power 6, already given, okay, for us. Then times the inertia, which is going to be pi 1 inch, right, to the power 4 over 4, because we are talking about a rod, okay, it is circular section, okay, over 10 times 12, which is the length of the beam in terms of inches. Take care of the unit conversion. 10 times 12. So 12 here, it is for conversion. Okay, from 1 foot to equal 1 foot equal to 12 inches. Okay, so now we have this. If you calculate this, you're going to find it giving you 39.54 pound per inch. Okay, take care of units, as I said. Based on this, our K effective is going to equal, okay, 20 pound per inch times 39.54 pound per inch over 20 plus 39.54. This gives us at the end 13.39 pound per inch. Okay, this is the K effective that we want to have, and then our final equation of motion, it is going to be, this is the equation of motion. So K effective, we're going to put this number instead of putting K effective. Okay, so the point here is, I think that I have, is it so? It is going to be mu double dot plus 13.39 u equals to P of t. This is our equation of motion. Everything in terms of t, okay? And we know P of t if it's given, and m also we know it. Okay. One thing that I want you to be aware of, that K of the spring, how much here? 20, right? K of the beam, how much? 39 plus something, or 39 point something, almost 40, right? So we have K beam is almost 40, K spring is almost half of it, 20. But how much K effective? 13.39. It is less than the least of them. Can you understand this? This means that if we have a system with a beam, this beam is having strong stiffness, and like as it is here, it is almost 40, and we are going to attach another system or another spring that is weaker than it, which is having stiffness of 20. The whole system is going to work as one spring, as if it is one spring with stiffness equal to, K effective equal to 13.39. You understand this? So this is very important concept for you, that if you have a system that is containing of two different elements, both of them, they are having high stiffness, but one is less than the other, okay? You're going to find that the combined effective stiffness of both elements or this system is going to be less than the least of them. Understand? The stiffness is going to be lesser. Okay? You understand my point? This is an important issue for understanding systems, especially for structural systems, that we are attaching elements to one another. So we need to understand that the effective stiffness of the system is going to depend highly on the individual stiffness of each element and the contribution of the stiffness of each element. Okay, you understand? Okay. Okay, so this is the first example, and let's go to the next example, which is going to be related to this is like, as we said, the pendulum. Okay, so this is another example, which is example 2. Okay, so we want to determine the equation of motion if we have something like here. So we have a pendulum, as you can see here, and this point, we're going to call it point O, and we have some dimensions, for example, given for us, which is L. The length of this pendulum is L. We have the mass M here, and this is, we are going to say this is light string. Okay, so this is light string, means that there is no mass for it and it doesn't carry any compression. It's only light string. So we have this mass, and we have the fixation at the top, and we want to derive the equation of motion. So determine what is required here is determine the EOM, the equation of motion, of the free motion of the free motion of the simple pendulum. Simple pendulum. So we want to have this this equation of motion. Okay, now let's go and try to understand what is going to happen for this. First of all, this pendulum, whenever it goes, its motion is going to be something like this in the circular orbit. Okay, so in this case, we are going, whenever that we have a body that is moving, okay, in a circular orbit, Okay. Assume something like this here. Okay. And we assume that here we have our spring, and this is the, okay. So here we are going to have, for this mass, we are going, first of all, we need to understand what are the forces that is being applied in this system, okay, under motion. So if we give this system a push, for example, and then leave it to freely rotate, okay, we want to get what is the equation of motion that is controlling this motion in mathematical form. So first of all, whenever we are going to do so, we need to understand what are the forces applied in the system, right? So if we have a mass with M, the first thing that we are going to put is what here? What is going to be down here? It is weight, right? The weight of the system, or the weight of this object, which is going to be m dot g, right? And whenever that we have this m dot g, we are going to decompose this force downward. We're going to compose it into two perpendicular directions. That is going to be easier for us to calculate, which is going to be, let me put it in another color here. So we're going to put it in the tangential and perpendicular to this tangential, or radial. Okay, we're going to have these two components here, and this component is going to be here, it is going to be mg cosine theta, where this theta is going to be the angle between the string at the point of motion that under consideration and the vertical line. And the other one here, which is this, and this one, it is going to be mg sine theta. So now we have composed this system, okay, decomposed the force or the weight to be like two components. Okay, now what else that is going to have forces here? Is there any other additional force that is going to be present here? If we have a mass that is going back and forth like this, what will happen? There is motion here. What will happen for this mass? What will be induced? Yes? The what? Yes, so yeah, that's right. So there is something in the string. Okay, yes, you're right. So there is something that is well developed in this spring, which is what? Like tensile force that is bringing this mass and keeping this mass, okay, to be maintained in this motion. So we're going to have T here. That's right. Okay, but this is in the radial direction. What about other thing? What will happen for this? Did you experience putting yourself in a swing and someone is giving you a push? Right? What you're going to back, forth, and enjoying this, right? What will happen here if you are going back and forth? What you are going to experience? If someone tries to stop you, what you are going to do? If someone is like withdrawing you like this, what will happen? You're going to go in this direction. This is inertia. This is inertia force. Right? So in this case, we are going to have inertia force. Let me put it in another color here. Okay, this is this color, or let me put it in another nicer color. Okay, this one. So we are going to have inertia force opposite to the direction. If we say that the direction of motion is in this direction, for example, then we are going to have inertia force that is going to be in this direction. Okay, this is, we are going to call it Fi, which means that F inertia. Okay, and this F inertia is going to be decomposed into two components. One component is going to be radial, and other component is going to be tangential, right? We're going to have two components here. Okay, so we're going to call this one to be Fi with the subscript n, which means that normal. And the other one is going to be Fit. Fit means that tangential. Okay, so we have two components, normal and tangential. Okay, that's good. Still, we didn't go to the equation of motion, just we are understanding what are the forces there on the system. Okay, so now it's very nice for us to understand these forces. Let's go and recall something here that we want to recall it because it is going to help us in this work. Whenever we have any object that is moving in an orbit, okay, there is two different acceleration are going to be developed. The first one, we call it alpha tangential, which is the tangential acceleration, and it equals to r times theta double dot, where r, in our case, it is this length, which is L in our case. This is r, for example, from here, okay, to here, this is r, the radius, right? And alpha, normal, okay, it is going to be r times theta dot squared, okay? This means that we have this mass that is going back and forth. It will experience two different accelerations. The first one is normal, and the second one is tangential, so that it will keep this kind of motion, okay? So we have these two, okay? Well, so this is generally whenever that we have any object that is moving like this, and we have r here, and this is m. So here, this is the tangential, and here, this is alpha n, and this is alpha t, okay? In general. Okay, that's nice. Just keep this in your mind now. Okay. Theta dot that we are talking about, we call it angular velocity. Angular velocity. And theta double dot, it is going to be, we're going to call it angular acceleration. Okay, angular velocity and angular acceleration. Whenever we have two different, or whenever we have this theta, we have two derivations. Theta dot, which is the velocity, and theta double dot, which is the acceleration. Okay? Okay. Now let's go. So let's go to the application of what we have studied before. So I'm going to write it like this: by applying D'Alembert's principle. D'Alembert's principle. Do you remember this D'Alembert's principle? Okay. With, as we have mentioned before, with fictitious inertia term. With fictitious term. With fictitious inertia term, and taking moment at point O. Where is point O? Here. This point. Here. Okay? This point O already, which is the point of fixation of our system. The point of fixation. Okay? So, first of all, I want you to read these two lines that I have read here, that I have written here. By applying D'Alembert's principle. In D'Alembert's principle, we usually apply the fictitious inertia force. We say that without thinking too much, whenever there is a motion of one object, there is inertia force is going to be developed. opposite to the direction of this motion. If we are talking here, so the fictitious inertia force is going to be in the opposite direction. Okay, so this is the meaning of applying D'Alembert's principle with friction term and taking moment at point O. We're going to take the moment around point O or at point O, which is the fixation of the system. Okay? Okay, can you help me in writing this equation? Taking the moment around, so let's assume, or let's have, by summation of the moment at point O, it should equal to 0, right? Because we are dealing with what? We're dealing with dynamic equilibrium. All these forces that you can see over there, they should be in equilibrium at each time, at each point of time. Okay? So, okay. Now let's go to this equation, or taking the moment. First of all is the term of the inertia force. The inertia force, look here. The inertia force is going to have two components, right? One component normal, which is Fin, and another component is tangential, right? Which one is going to make moment? Fin or Fit? Fit. Yes, Fit, right? Because it is having an arm, and this arm can make moment. However, Fin, will not make any moment because it's radial. Okay? Okay, now let's go and write this. That, which is F I T, and you understand what is the meaning of T now. Okay, times the arm that is going to be there. The arm, it is the radius, which is L in our equation. It is L, right? We are talking about the length L. Okay, now plus what else that is going to make moment? So now the inertia force is already, we finished it. The two components finished. Now the second force is what?
mg sine theta.
Yes, we have the mass, we have two components, which is mg sine theta and mg cosine theta. Which one is going to make the moment? Yes, mg sine theta. Okay, so in this case, let's say that the weight, which is going to be component of the weight, mg sine theta, this is one component of the weight. We call this weight component. Okay, times what? Times what? The also the same, which is related to L, is the, as if it is the radius. This should equal to 0, right? Then we're going to put the inertia term here, Fit, it equals to L theta double dot times M. This is the inertia term here, and then times L plus mg sine theta dot L. It is the same here, equals to 0. Right? You understand, of course, Fit came from where? Okay? As I mentioned, recall this, alpha t and alpha n, and the inertia force is going to be, Fit, it is going to be based on alpha t. So we are going to have r theta double dot. R here, it is the L, which is the length, right? So we have L theta double dot, because this is the tangential one, times m, the mass, times L, which is the arm that is going to make the moment. Okay, now we are going, as you can see, we're going to find some common terms here. Okay, some common terms, and these terms we can rearrange it. So if we're talking about small thetas, for small theta, we know well that theta equal to sine theta. If our pendulum, okay, is going to have like very small theta here, so mathematically we can say that theta equal to sine theta, and based on this, we can say, after rearrangement, theta double dot plus G over L times theta equal to 0. This is our equation of motion. Equation of motion in this case. This is the equation of motion in this case. Okay, you understand this? Okay, any questions up till now? Is it clear for you? Yes?
I will get this inertial force
Hmm.
and angular velocity from where this m comes.
L double dot, you mean here? L theta double dot.
And
Sorry. Because, okay, this part, which is L theta double dot, it is alpha tangential, which is acceleration. We need another term, which is mass, to be multiplied by this acceleration in order to obtain force. So the first two, L theta double dot, it is acceleration, m, it is mass times acceleration, it is force. Okay? Okay, now let's go to the next and the last example in our first class, okay, which is example number 3. Okay, here we are going to have this system that is, as you can see here, we have a system like this, and we have like rotation here, okay, and this system, let's put it at the dimension of this system, it is L, and we have the spring stiffness, which is rotation stiffness of this system, we call it rotation stiffness of this spring, it is with a constant K, and we are assumed this to be rigid. It is rigid and massless rod is going to be there, and we have the weight of this mass is, or the weight of this object is W. We're going to assume small deflections. We're going to assume small deflections. Means that we're not expecting that this rod to go in or to have very high deflections. It's only something like this, okay? It is small deflections. It's important actually to keep this assumption. Assume small deflections. Okay, so now our point is derive the equation of motion. Derive the equation of motion for this system. Okay, for this system, small deflections, and we said that whenever we have system like this, so derive, what is required from this is derive the EOM, the equation of motion for this system. Well, we need to understand what are the forces being applied here. So we're going to assume that our system, which is, this is the rod here, and this is the mass here, and we have this orbit, which is going to be like this, and we are going to have the forces applied, which is, first we have the weight of this system, and as we mentioned before, that whenever we have motion, this means that we have inertia force. So we are going to have in some way or another inertia force, F inertia. So imagine that this system is going to move to the left or to the right slightly and then keep it. Then it will make something like this. So we need to know what is the equation of motion that is going to control this motion. So first of all, when it moves, then this mass, it has vertical weight, right? Which is W. And then whenever there is motion, as we said, there must be a kind of what? Inertia force. So the inertia force is going to be as you can see here. Then we're going to decompose this inertia force, as we have done in the previous example. It is going to be two components. Okay, this point, it is point O, it is the original. Okay, two components. We have Fi tangential T and Fi normal N. Okay, and similarly for the mass, let's have this color, for example. For the mass, which is for the weight, we're going to have two different components. One component here and another component here. This is going to be W sine theta, where theta is here, and this is going to be W cosine theta, right? It is two components that we have here. Okay. So first of all, we want to have the equation of motion for us. So we know that our system has this rotational stiffness, I mean that of the spring. So we have spring, okay? And in the same time, the Fs is going to be, or the resistance of this system is going to come from this spring only. Let me ask you a question. This beam here is going to contribute or not? The beam, this rigid massless rod, if we call it rod here, rigid.
For controlling the reflection?
For the deflection, yes, we call it rigid massless rod.
Yes.
It will contribute. Okay. What about you? Okay, what's your name? Ali, okay. Okay, and what about others? What is your name? Melis. Okay, what's your name? Sanjwa? Sajong. Okay. Okay, and Bian. Okay, so what do you think about this? So this rod is going to contribute or not? Melis will not contribute. Why? What is the reason? It is massless, but this is not the reason. The reason is, yes, it is rigid. Yes. This is very important thing. This is why I said take care whenever that you are looking to the examples, take care of the wording. Massless means that there is no contribution for the mass of the system. So the mass is concentrated at the top. And rigid means that this beam is not going to make something like this. It is rigid. It is always rigid. It's not like the previous example. Okay? The previous example, the system itself, I mean that the beam was deflecting. It was constant from here and it was deflecting like this. But here we said that it is totally rigid. So here, this line, it is going to be like rigid body motion, rotational. Okay? So this is why we say that we're neglecting the rotational stiffness of this rod. Okay? This means that the stiffness, rotational stiffness of the system is going to come primarily from what? From the spring. Okay? This spring at the support, but it's not going to come from the rigid rod, right? So in this case, we are going to say F of S, or the resistance force of this system, is going to equal K times theta. Okay, K times theta, right? This is K, take care, it is rotational spring stiffness. So I'm going to give this definition. It is the rotational rotational spring stiffness. It is the rotational spring stiffness. Okay, and Fs, as we said, it equals to K times theta. If the other force that is going to be there, so we have here, there is Fs is going to be developed in this system, and it is going to be developed at or around point O due to the spring only. So now the system is having weight and having inertia force and having Fs, which is restoring force of the spring at the bottom, right? We have three different components. So in this case, we're going to say Fi, which is the inertia force, Fi T, which means that tangential only, okay? Ft here tangential, okay? It equals to m theta double dot times L, right? Because we're talking about L. M, okay? M dot theta double dot, Ali, M mass times theta double dot, as we said before, because we are talking about the tangential, times L, which is going to be the arm. It is the arm, okay? So in this case, we are going to have, so we have here, this is theta double dot L, this is like alpha tangential, and this is the mass of the system, so it gives us the inertia force. Now let's take equilibrium, okay, at point O, which is the origin, okay? We are going to have different forces here. The first one is Fi tangential. It is going to be m dot theta double dot times L, right? This is the inertia force times the arm, which is L. Okay, so we're going to take the moment. Let's put it here, summation. Sorry for this. So we are having the summation of moment at point O should equal to 0. So now this is the contribution of the inertia force. This is the inertia times its arm, plus, let's go back to our color, so plus the Fs, which is the restoring force of our system, which is going to equal to K times theta. K, it is the rotational spring stiffness. Theta, okay, it is going to be the rotational angle, right? So this is what we're going to have. Then it should equal to what the contribution coming from the weight, which is going to be the W sine theta times L, right? So I'm going to put it like this, mg, which is the weight, times sine theta, which makes the tangential component of the weight, right? Times L, which is going to be the arm. We're talking about the arm here. Okay, so because this is this length, this is L. Okay? Now, after rearrangement, we can rearrange this equation, the last equation, and we are going to have this nice equation at the end, which is m L squared theta double dot plus K minus m dot G times L, all of it, times theta equal to 0. Remember that we are talking about small angles. Okay, so we are talking about small deflections. Theta should equal to sine theta. Okay, so remember that sine theta equal to theta. We are talking about small deflection or small angle rotation. Okay, So there is something that is very important here. Okay. One of the most important things that I want you to know and remember that, as I said, this rod is not going to make any rotational stiffness because it is rigid and it is hinged at the bottom. This is number one. Number two is, look to this equation and look to this sign. It is minus. It is minus here. So what is the meaning of this minus sign? This minus sign here that we are having. What is the meaning of it? Anyone can give me a definition for the minus here? mg is what? mg is what? It is the weight. K is what? Rotational stiffness, right? Well, what is the meaning of this? In this equation, in order to be under equilibrium, assume that the mass is increasing, what will happen here? If the mass is increasing, mg term is increasing. Yes, that's right. Stiffness will reduce. Take care of this. Can you imagine what is happening here? This is the rod, and this is the mass here, and we are making small deflection. But what if there is someone making like this, and then it goes like this? When it goes like this, the weight is going to reduce the restoring force. Understand? Here it was making like this, but when it goes like this, it will be difficult to come back until it reaches to point. This point is what? Failure point. Resistance will not be there. It will not go like this. It will fail. Okay? This is very important. This is very important, and we say that this sign, the gravity, we're going to say that the gravity load reduces the effective stiffness of the system. That's very important. And we can say, this is a very important note that we can end up with, that if the second term in the equation of motion is 0, this is the second term here, okay? If the second term in the EOM, the equation of motion, equals to 0, what will happen in this case? This means if the second term equal to 0, if exactly K equals to mg, what will happen for this system? It will be what? Failure. Why? Because this term is going to vanish, and this means that the first term, ml squared theta squared equal to 0, which is impossible, right? This means that failure of the system. The mathematics is not going to work here. Okay? So this means that, this means unstable system. Unstable system. Okay? This means that the system will be unstable under its weight. Or the system is unstable under its weight, which is the case that I have explained to you, that the mass is not going to find restoring force anymore. It will fail. So the critical weight, we can say the critical weight for stability is, I'm going to put it like this, W critical should equal to K over L. This is W critical. Look here, if this is the weight here, this term is the weight, right? So F equal to K over L, in this case, this is the critical value that we should not go beyond. Otherwise, it will make the second term to be vanishing, and then the equation will not be stable. Okay? Understand? Is it clear for you? Okay, we'll stop here for the first lecture and see you in the next video.